Okay. So in this lecture, we'll talk about a very interesting topic on two energy level system, and we'll talk about the negative temperature. You will see that this concept of negative temperature, by understanding the concept, you will come to know that, see, negative temperature is actually hotter than the positive temperature. Okay, which may appear to be very funny at the outset, but I will see that actually if you keep a system which is at, let's say, positive temperature and one at negative temperature, and if you try to establish thermal equilibrium between these two systems, you will see that the heat or the energy will flow from the negative temperature to positive temperature, because negative temperature system is much hotter than the positive temperature system. Okay, let's start the discussion. So first we will talk about two energy level system. Okay, so now consider a system having two non-degenerate microstate with energy epsilon 1 and epsilon 2, let's say. So we can talk about, let's say, a system which is having two energy level. Okay, and it is non-degenerate, meaning it has got only one energy state within the energy level. Okay, so this is for our simplicity, and let's say the energy associated with this is E1 or epsilon 1. So I will sometime just meaning sometime I will call epsilon 1, sometime I will E1. So just to be ensured that this is one of the same thing. Okay, so this is E2, energy E2. Okay, and the difference, as it says that E equal to E2 minus, so the difference between these two energy levels, energy states, it is E. Okay, and we will now consider that this system which we are considering, we will talk about a very specific system as after a few slides. Okay, so let's try to establish the problem. Okay, so let's say this system is in thermal equilibrium, okay, at temperature T. So we can write down the partition function for the system. Okay, so what it would be, it has got only two energy levels, so energy states of the system. See, we have tried writing partition function for similar system in the previous videos as well. So let's try to write down here. Okay, so Z is my partition function. Okay, it will be e to the power minus E1 by KT. This is the first for the first energy state. Secondly, e to the power minus E2 by KT. Okay, so we can write down the partition function for this. Let's see. Yes, it is written here. Okay, so this is the partition function that we can write for this system. Okay, now let's discuss about the probability of occupancy of these states. Okay, so it has got two states, right? So system has got, let's say, two states as we have discussed earlier. Okay, so if you have a particle which, see, the probability associated with this state, like which is so if it is in the E1 state, what is the probability of occupancy of that state, which we have talked about in lecture number 9. You can go back if you are and watch that part of the lecture, and again come back if you are not familiar with this expression. Okay, so that is given by P1. So basically it is the e to the power minus E1 KT by the partition function. Okay, so this is what it is written here. So, and you substitute for that, and then what do you do in this expression here, or the term here, you divide this numerator and denominator by e to the power E1 by KT. So on top, that is in the numerator, and the denominator you divide by this term. Okay, and you will end up getting this. Let me just see, erase this. Okay, so here T got dropped. Okay, so you will end up getting this expression. Okay, then similarly for the other state, the higher energy state, we can write down the probability, that is P2 here, e to the power minus E2 by KT is by Z. So I substitute for the Z here. Again we divide numerator and denominator both by the same expression that we had divided in the earlier. Okay, e to the power E1 by KT. Similarly here in the denominator we have divided by E1 by KT. So after doing that division, we'll ended up getting this expression. Okay, so then we define a new variable, which is, let's say, theta, now which is equal to E2 minus E1 by K. See, if you do a bit of dimensional analysis, you will realize that, okay, so this part has got dimension of temperature, isn't it? So you can think about a new scale. Okay, so in the meaning theta scale. Okay, so theta has got, so it's a new variable we have defined, and it has got a dimension of temperature. Okay, so we have seen the P1, so the nothing we have done is substitute for theta. Okay, so P1 has become like this, P2 has become like this. So what we have realized that, you know, the P1 and P2 depends on temperature. Okay, so now let's try to analyze a bit. So you can always have two extremes of the temperature. Let's say temperature equal to 0 or very high, let's say it's infinity. What will be the occupancy or the of the state, or the P1, the probability of occupancy of the ground state or the E1 state, and then probability of the high energy states. So for the system that we have considered, we have considered two energy level system or two level systems. Okay, system which has got only two energy levels. Okay, so if you do a little bit of analysis on this, let's assume that temperature T is equal to 0. Okay, so in the scale of temperature that we are trying to understand here, let's say T equal to 0. So what will happen if I substitute T equal to 0? So the theta by 0, which is going to give me infinity, and this is, you know, like e to the power negative infinity, which is like, you know, 1 by e to the power infinity. See, the denominator itself here is a very large number, so I can assume that this number is nearly 0. 1 by a very large number is, which is going to be infinity, so 1 by infinity you can think about it like a 0. Okay, even though infinity is not a meaning number, so just it's a very large number you can think about. Okay, so ultimately what I will get, this expression here is 0. So the probability P1 will be then 1. Okay, so I can think about it, I should not write equal to 1, it's nearly equal to 1. And if you substitute back the same expression, e to the power minus, so we have got what, for a case of t equal to 0, e to the power minus theta by t, so this expression actually turns out to be 0, isn't it? So then what will happen? For this case, P2 will be equal to 0, or it's very negligible, it's a pretty small number which is nearly equal to 0, isn't it? So at temperature T equal to 0, the probability of occupancy of the E1 state, also called the low energy state, is higher compared to the high energy state. Okay, so it's almost 1, you can think about. All right, so yes, so you can talk about like system is in ground state, you can think about. Okay, so now this means what? If we keep on increasing the temperature, so the idea that the understanding here you can think about, if I keep on slowly increasing the temperature from 0 to slowly, if I increase, that means the probability of the high energy, the probability of occupancy of the high energy states increases. Like P1, which was P2, which is initially 0, slowly it will start increasing. Okay, so the value of P2 will increase from 0. Okay, if I increase temperature gradually. Okay, all right, so then that's what it is again. So in the scale of theta, okay, so when theta is much greater than T, that means the temperature is much smaller than the value of the theta, which means that, see, the theta was equal to what? E2 minus E1 by K. Okay, so if, so you can think about, so this is like difference is E by K. Okay, so I can write, you know, when this from this expression you can think theta is much greater than T. Okay, so I can substitute here what? If I substitute this theta from this expression, okay, so I will be getting theta, temperature T much less than E by K, which gives me
T, this is KT E by, sorry, this is E, simply E, right? So the energy difference between the two levels is much greater than the temperature. Means what? Even if the particles which are present at the ground state, so thermal energy is not good enough to take them from the ground state or the lower energy state to the high energy state. That's what you need to understand, because this energy is, the gap between the two states is so high that the temperature, that the energy which is being supplied to the system from the temperature, there is a thermal energy, is not good enough to carry the particles or molecules, atoms which are lying in the E1 state to the high energy state. That's what you need to understand. Okay, so that means what? P2 is the probability of occupancy of the higher energy state is negligible. Okay, and this begins to increase when the temperature is increased. That's what I said in the last slide. All right, so then let's come back to, now let's discuss about a system, okay, which is a paramagnetic substance. Okay, so let's consider a system containing paramagnetic substance, okay, which has got n magnetic atoms per unit volume, okay, and which is placed in an external magnetic field. Okay, so let's take a unit volume of a substance and which has got n paramagnetic atoms, and we consider that each atom has got only spin half. So these atoms have got spin half. So moment you have spin half, so we can think about, like, whenever I place in a magnetic field, either it will be aligned, this magnetic moment of this meaning these atoms will align either parallel to the external magnetic field or anti-parallel. Okay, so and each of the atom has got magnetic moment mu b. Let's discuss about that. Okay, so let's take mu b is the magnetic moment of each atom. So as I said, on application of magnetic field, so what will happen? So there is a magnetic energy which is will be developed in the system, and this is given by the magnetic energy of an atom in an external magnetic field is given by, so actually this is minus mu b dot b, and which comes out to be minus mu b cos theta. Okay, so theta is the angle between this magnetic moment and external magnetic field. And as I said here, either this magnetic moment of the atoms will be aligned along the magnetic field, or it will be opposite to that. So there will be parallel or anti-parallel. So when it is parallel, so theta will be 0. In that case, so if for the case of parallel, either it will be in upward direction or both of them in a downward direction. So energy of the ground state you can think about, or the lower state, E1 is given by minus mu b b. Okay, b is the strength of the applied magnetic field. Now for the case of anti-parallel, or the direction between magnetic moment and the magnetic field that is we applied from the outside, and if both of them are anti-parallel, then this is, the theta is pi, so the cos pi will give you -1, so that -1 and this -1 will become now positive, like +1, so that's why we get mu b b. Okay, and as you can see that, so this you can think about these two states. Okay, so the lower energy state having the energy E1, which is minus mu b b. Okay, so this lower energy state contains the atoms which are parallel to the magnetic field. Okay, so these are, so here you contain parallel. Okay, so the parallel to the atoms which are parallel to the magnetic field, whereas on the high energy state, which E2 we can think about, mu b b, it has got higher energy, and here atoms are anti-parallel to the applied magnetic field. Okay, now I can write down the partition function which you have already written, okay, earlier. So just substitute for E1 and E2, which I ended up getting 2 cos hyperbolic mu b by kt. So if you are not familiar with this cos hyperbolic function, so cos hyperbolic x is given by e to the power x plus e to the power minus x by 2. Similarly, we will also have sine hyperbolic as well. So where in the only this positive term will become negative in the sine hyperbolic case. Okay, so then I will get, this is cos 2 cos hyperbolic mu b by b. Okay, and assuming that the system is in thermal equilibrium at temperature T. Okay, so then I can, yes, so let's say there are, so out of these n atoms that I have considered for our system. So I'm taking only, so the N was the number of molecules or the number of atoms per unit volume. So let's consider only one unit volume of the substance. So I have N atoms in there. Out of that N, we assume that let's say N1 are in the ground state, I mean the lower energy state, and N21, this is lower energy state. So here atoms are lower energy state. So atoms are parallel to the applied magnetic field. Okay, and N2 numbers are in the upper state, which are anti-parallel to the, okay, so higher energy state, let's say higher energy states. Okay, and N1 plus N2 is equal to N total N. Okay, so the probability of this N1 and N2, so how much of like we can calculate out this N1 and N2 values for that. So the if N1 and N2 are number of atoms whose moments are parallel and anti-parallel to B, as I say, so N1 are this number of atoms are parallel. Okay, so it will be given by Nz by this expression exponential mu B by B. So this many atoms are actually in the lower energy states, whereas because here see the exponential, this is actually exponential minus of minus mu B by kt. So it may okay, so that's why it is now meaning becoming positive here. Okay, so in N2 case, so it is the number of atoms which are in the higher energy state. So from here itself you can see that this N1 is greater than N2, right? Because there is this negative term. Okay, N2 will be lesser than N1. Okay, value of that if you compare both of them. So N2 is given by N by Z exponential this term. Okay, so then now I can calculate the wait. So this N equal to N, then yes, all right. So I can calculate the what I'm trying to calculate the magnetic net magnetic moment of the substance. Okay, so let's calculate the excess atoms which are aligned parallel to B. So the N1 atoms are aligned parallel to B, and then N2 are number of atoms which are anti-parallel to B. So if I do N1 minus N2, so I will get number of atoms which are excess atoms which are parallel to the B. Okay, so in that case I just simply substitute for that. Okay, so I end up getting this. So here I use sine hyperbolic function. As I said, sine hyperbolic is given by x is given by e to the power x minus e to the power minus x by 2. Okay, so then okay, so using this particular formula I get sine hyperbolic. Okay, all right, so now I can calculate so then so next what I do, I substitute for this z. So z I have already calculated here, right? So that z was 2 cos hyperbolic and then mu b by kt. So if I substitute for that, substitute for z here, so then I will start getting, you see here z was so 2n. Okay, so in the, so it was 2 cos hyperbolic it was, right? So it was sine hyperbolic of this particular. So I am not writing this one. Okay, you can see what I am doing here. So this is cos hyperbolic of the function. So 2 get cancelled out, n remains, and sine hyperbolic by cos hyperbolic is given by tan hyperbolic, which is this. Okay, so now I can calculate net magnetic moment of the system, which is the mu b into the number of atoms which are I mean more like excess atoms which are aligned parallel to B. So from this expression I can calculate number of the net magnetic moment of the system, right, which is given by n mu b tan hyperbolic mu b by kt. Okay, so let's, having this information intact, okay, let's just go back to what we have discussed about increasing temperature and then the probability of occupancy increasing and things like that. Okay, so just wait a bit, we will come back to this example again. So now let's consider, okay, so this is now normal case. Okay, what happens? So if you take a perfect gas or the ideal gas, and if you consider a molecule or an atom of a perfect gas, So it has got infinite number of energy levels. Because the perfect gas, it is not experiencing any potential, so it's not bound to anything, so it can occupy or it can take up any energy level. So if you keep supplying energy, it will take up energy, so it can be present in any of the energy levels it has. Okay, so as the temperature of the system, so this perfect gas system, ideal gas system, more molecules will occupy, are raised to higher, so more molecules are raised to higher energy states, resulting in greater disorder. So you can think about, let's say, so if I take only single molecule, it has got, let's say, lots of energy levels. So initially, let's say it is lying in the ground state. Simply keep since it can go to any of these higher energy states, if I supply energy, depending on how much energy I supply, so it may occupy, let's say, go to next side, let's say, or maybe somewhere else. Okay, or maybe it can take up even higher energy states. Okay, now let's say I have not only one atoms or molecules, I have, like, thousands of molecules of that. Okay, so I have so many of them lying here, and if I keep so initially all are lying in one state, so there is an order in the system. Now if I keep supplying energy, or if I raise the temperature of the system, what will happen? Slowly, depending upon its probability, then how much of those atoms can absorb energy, depending on that, it will keep on going either to this state, or maybe some will go to some other state, like that. What will happen? So it will start increasing the disorder of the system. So that's what it is said. So it will be the if it increase the temperature, more and more number of molecules or the atoms present in the ground state will slowly go to the higher energy state, and then the order will increase. Okay, so that's what typically happens, which we are accustomed to in our basic thermodynamics. Okay, so if you remember this thermodynamic relation, so dq, or let me write, because it's not a proper thermodynamic function, so del q, which we know that TdS. Okay, so this relation we are accustomed. Okay, if you think about it, even if you internal energy equal to TdS, all these things. Okay, so if I supply this energy, okay, if I increase the energy, so in this scheme of things that we are trying to understand, entropy is increasing because the disorder is increasing, so the entropy of the system is increasing. So if I increase the energy, entropy increases, that means the temperature here is a positive quantity, isn't it? So meaning that's what is happening. Okay, so, or in some case, if you write the internal energy du is equal to TdS, if I increase the internal energy of the system, entropy is increasing, so it is give me a positive slope, so the temperature T is a positive quantity. Now, keeping these things in mind, get back to the system that we have discussed few minutes back, okay, which is paramagnetic atoms, which have got n atoms. Okay, out of that that n1 had occupied the low energy state, and then n2 had occupied the high energy state. So the probability of, or occupation number of these two levels is given by this particular expression that we have discussed already. Okay, so E1 is the energy of the lower energy state, okay, the ground state if we talk about, and this E2 is the high energy state. Okay, and see here we are talking about only two level systems. Okay, so two energy level system, where this n1 is equal to the n is equal to n plus n2. Okay, so having known about its occupation number, what I can do, I can take a ratio of both of them. Okay, then I can calculate an expression for temperature. So from here, what do you do? Take ln on both sides. Okay, I think it is pretty straightforward. Okay, so at the other side I'll get E2 E1 by KT. So from this expression I can get this temperature relation. Okay, so in this case, what is so I had these two states, where this down the low energy state has got E1, high energy got E2. Now these N1 atoms are parallel to the external magnetic field, and this N2, the other number of atoms which are anti-parallel and has got higher energy. Okay, so these atoms are in higher energy states. Okay, so according to this expression here, So for the case here, since E2, the energy E2, okay, this energy E2 is greater than E1 because we have considered. So, and with the number of atoms, N1 is greater than N2 for the case. So wait. So since we know that E2 is greater than E1, and if the case for which N1 is greater than N2, which is usually the case, the temperature will be a positive quantity. Because this N2 in the denominator, N2 is greater than N1 is greater than N2, so the denominator is a positive quantity here, and E2 is greater than E1, so both it will give a positive number. So temperature will be your positive quantity. Okay. Now you must be thinking, why am I talking so much about, like, positive temperature, positive temperature? Now come back to the case. Very interesting thing is going to happen. Okay. So let me take, okay, let's switch the direction of magnetic field instantly, let's say. So let me draw the earlier case. Okay, so we had this case. Okay, here this N1, N2, and this is E2, E1. So in this case, N1 number of molecules which are parallel to magnetic field, parallel to, let's say, B, and N2 is anti-parallel to magnetic field. Now I have switched, and then here I know that E2 is greater than E1. Okay, this is the case here, and here the temperature is positive for the case where N1 is greater than N2. Okay, now I have switched the direction of magnetic field. So what will happen? What was initially parallel will become now anti-parallel to the magnetic field, and what was initially, or in the first case, the atoms which were anti-parallel to the magnetic field will now suddenly become parallel to the magnetic field, isn't it? Okay, then what will happen? Okay, let me just draw the same. Okay, so the number of these N1 molecules or the atoms which were initially parallel, now it will become anti-parallel to the magnetic field because I have switched the magnetic field. So what will happen? Now it will be, suddenly it will feel that its energy state is higher. Okay, and N2 molecules which were initially anti-parallel to the magnetic field, now it will become parallel, and which will having low energy states, isn't it? Because now the parallel, if atoms are parallel to the magnetic field for a paramagnetic substance, so what will happen? For that, the atoms which are parallel to the magnetic field has got lower energy states, so it will have lower energy corresponding to the meaning the anti-parallel atoms. So if I have to draw in the scale where your lower energy state is my bottom, the down level is my less energy state, and upper level is the high energy state. So in this case, what I will flip the thing. Okay, so what I'm trying to say here is that, so now this E1 state is now high energy state when I switch the magnetic field. Okay, and the E2 case, which has got now N2 number of atoms, okay, which is the low energy state. Okay, but still see, so still what happens is N1 is greater than N2. So still the case N1 is greater than N2, because what has happened? I have switched the magnetic field, nothing has happened. Okay, suddenly, so this case is called as population inversion, meaning if I can somehow make the situation where that high energy state, so the number of molecules or the atoms in high energy state is more than the low energy state, this is like switching of the population. Okay, so this is population inversion, which is typically used in the laser, okay, theory of laser. Okay, so now, so for the case N1 greater than N2, so I have realized that now E1 is greater than E2 from the discussion that we had. Now let's go back to the temperature expression. Okay, let me clean off here. Okay, so Still what happened is N1 is greater than N2, which we have already, but the case here, E1 is now greater than E2. E1 is greater than E2. Why? Because the molecule or the atoms which were initially parallel to the external magnetic field, so we were in a low energy state. Now because I have switched the field, okay, so these atoms are now higher energy states. So E1 is greater than E2. So if that's the case, denominator is positive, no change. However, on the numerator, as you have seen here, okay, E1 is greater than E2, so it will lead to a negative temperature state. Sorry, here yes, negative temperature state, isn't it? So on switching this field, we have got a condition, okay, of the state where the higher energy state has got more number of atoms compared to the lower energy state, which is called as population inversion. But as a result, what we have got is negative temperature. Okay, so from the temperature expression I have got. Now same thing can be thought about. Okay, so it's like, you know, let me just clean up. We need to understand this a little more. Okay, so from if I take these initial conditions, okay, so I have two state. Initially, let's say all atoms are in the ground state. Okay, I slowly keep on increasing the temperature. Let's say there are N1 particles. Initially all of them were here. I keep on increasing the number, so increasing the temperature. More and more numbers are occupying here. Okay, so what is happening? Disorder is increasing. Let's say I come to a state where this n by 2 particles are in the E1 state, okay, and n by 2, the remaining n by 2, so half of them are in the E1 state, the ground state, and the half of them are in excited state. So this state is actually the state of maximum disorder and maximum entropy. Because if I increase even one more from the ground state to the higher state, what will happen? Actually, I'm slowly decreasing the order. Because it's like, you know, I'm initially what? Suppose when there were more number of atoms here, slowly I'm trying to increase the disorder, right? Let's say here, if I have total of let's say 6 atoms, okay, so I have 2 states. Initially all 6 of them here, 6 of them, and I have one had gone there. Let's say one had gone there. So then the disorder is increasing. Okay, so now I come back to a state where there are 3 of them. Okay, now if I increase one more in the upper state, actually I have come back to a state here. So this is 4 in top and 2 in here, 2 in the lower state, which initially I had got from like here it was 4 2. One of the state will be like this in this case as well. So here I am, when on increasing 4 to 2, then next step will be 3 and 3 here. So I was trying to increase the disorder, but on further increasing the energy or the temperature of the system, when more and more atoms are occupying the high energy state for this system, such systems, so what is happening? Slowly, even more we are trying to increase the temperature. Okay, more and more atoms are occupying in the high energy state. Okay, it may appear that we are increasing the energy, so the disorder or the entropy should increase, but actually it is decreasing in fact. That's why what happens, even though it is a high energy state, the temperature corresponding to that, because the internal energy or that relation that I have showed you here, this is increasing, no doubt. Okay, but this is decreasing. That's why temperature is negative quantity, because slope is negative. Okay, but that corresponds to actually higher energy state. Okay, so that's why this negative temperature you can think about is hotter than the positive temperature. Okay, so that's what it is. Okay, this can be achieved on when we have population inversion in the system. Okay, So just to summarize, so for this we have done T equal to 0. Okay, so when the temperature was equal to 0, the probability of the P1, the probability of the ground state or the E1 state was 1 nearly, and all the atoms were in the ground state. N1 was 1, N equal to total number of atoms, and N2 was equal to 0. And all were in the ground state, so it has got minimum disorder and correspond to entropy 0. Okay, now on achievement of population inversion, what happened? Slowly this, when we increase the temperature, I'll come to a state that where the probability of the occupancy of both the states is half and half. Okay, so on the scale of, let's say, so I had said that this is E1, this is E2, and the difference was E. Okay, so on the scale of this epsilon or the E, I consider this is 0 and this is E, let's say. Okay, so initially the internal energy of the system, so when this temperature T was equal to 0, all atoms were in the ground state. So the internal energy of the system was 0. So internal energy, let's say I write E here, okay, capital E, 0. But on this state, whereas the P1 equal to P2 equal to half, so N by 2 molecules or the atoms were here and N2 were here. Anyway, this has got 0 energy, so the internal energy of the system is given by only these atoms, which is N by 2 on E. If I now increase more number of atoms from the ground state to this internal energy of the system will increase. However, the entropy of the system decreases. That's why we get negative temperature. And if you think that more and more number of atoms, which is this population inversion is achieved only by supplying extra energy to the system. There are so many ways, so many methods of achieving this population inversion. Okay, but somehow a external agency or external energy is required to supply to the system. Okay, somehow the internal energy of the system is increasing, but that is resulting in a negative temperature. So that's why this negative temperature is hotter or the higher than the actually positive temperature. Okay, I hope this is clear. This is, I think, it's one of the beautiful concept where you can, a very funny way you can talk about that, negative temperature is actually hotter than the positive temperature. Okay, we shall stop at this point.